So, I haven't quite finished this, but I've substituted -1 into this one that I put a little asterisk next to, and I've been very careful with my negatives because it's 1 minus -1 and so on. And I got this, 2, 4, 2, 4. Yeah? So obviously when we multiply at the top and the x, y, or the bottom, it's going to be the same. 2x plus 4y equals 0, so y is -1/2x. That would describe the line. Like that, I think. How do we get an eigenvector? Yeah?
The eigenvector is 1 minus 1/2 because we can put in 1 for x and then we can just find y.
Yep, if we make x 1, we can use this to find out what y is, so it would be -1/2. If you don't like the idea of having fractions, you can find a vector that has whole numbers. So I guess if we multiply them both by 2, we'd have whole numbers. I personally prefer that one, I think. But I got to it by making x1. Okay, so I think I'm gonna call my eigenvector 2, -1. So what we should do then is just to state clearly the eigenvalues and eigenvectors. So we had 1, 1, and lambda equals 5, and 2, -1, and lambda equals -1.
I think it does work as a shortcut.
Okay, you can show me in a second.
It works with this one as well.
I'm just going to highlight the bit that we jumped to because I saw Kirill highlighted it, so I want to copy Kirill. Because I think that is the key step. After that, yeah, it is a process. It's quite a long process that you need to learn. It's a really useful process to learn because it comes up in every session of exams. It comes up at least one time every session of exams. So you've got to learn it, okay? Because I guarantee you, can I say that? I'm like 99% certain it will come up in your exams this summer. This process, whether it's within another question or not, it will be in there somewhere, okay? So it's one we're going to practice lots and lots. It's going to come up in our next unit and we're going to practice it more then. We definitely need to learn it. Greta.
But what would like a word question with something like that look like?
We'll get to it.
Very theoretical.
Yeah, at the moment it's very, very theoretical. We will look at how this is used in our next unit with something called coupled systems. So where two things are changing related to each other. For example, a predator-prey system. And this helps us to understand how the system is changing. So that is one of the types of contexts that you'll look at it in. What was I about to say? Oh yeah, let's go back a few minutes. Greta was curious about this, where I said the determinant has to equal 0. Okay, let's go back to this bit that I put a star next to. If this had an inverse, we would just take the inverse of this matrix on the left and the inverse on this matrix on the right, and we'd multiply the inverse by 0, which will result in 0. So all we'll end up finding is that the point of the origin, basically. We'll get x, y equals 0, 0. Y, well, yeah, x equals 0 and y equals 0 will end up with the origin. So if we want any other results, we need to say that there isn't an inverse.
But is it about what we want or how to...
Well, okay, so from saying that there is an inverse, you get the fact that the origin doesn't change.
Yeah, but sometimes isn't it that there are also lines that don't have a point at the origin? So what would happen with that one?
Well, if all of the lines that we find as eigenvectors do go through the origin.
Do go through the origin.
They do go through the origin. And if we don't talk about the idea of it not having an inverse, we won't get those lines either. If we say that there is an inverse, the only thing you get is the origin from this.
Okay.
Because every time you're You're going to multiply the inverse by
Right, so
0.
we're assuming that it doesn't.
So we need to explore that as well, yeah,
Okay.
if we want to find the eigenvectors. Okay, the rest of this lesson is going to be practicing this skill a couple of times. Okay, so we have a couple of notes here. And I just want us to take the time to read them because this is a big algebraic, theoretical lesson today. So we're saying the real number lambda is called an eigenvalue of A if there exists a non-zero vector x that satisfies that. Eigenvalues are the solutions of this. This is the determinant of the matrix. It's the notation, Marina, that you were mentioning with the absolute values. And it's called the characteristic equation. Okay, I'm going to get you to try this example. I'm going to get you to try this example. And then we're going to have a little talk about this last one, because this is linking in with the example, the Kiko-Popsy example. Have you got general questions or individual ones? Okay, I'm going to stop the video.